All right, welcome back, everybody. This is section 5.1, Polygon Sum Conjecture. So we're starting out Unit 5 already. All right, so on this page it says, how many triangles can a quadrilateral be cut into? And as you can see, we have 5 different quadrilaterals here. So in parentheses it says, connect one vertex to every other vertex. All right, so let's go through and do this. So let's take our purple, what appears to be a parallelogram over here, and let's pick one vertex. So I'm going to pick this vertex right here, and I'm going to connect it to every other vertex. Well, obviously it's already connected to that vertex, so that doesn't count. And it's already connected to that vertex, so that doesn't count. So the only vertex left to connect it to is that one. And you can see that there are 2 triangles. Now let's go to our green, what appears to be a square. And we're going to pick this vertex and connect it across to that vertex. And again, we see 2 triangles. All right, let's go up top to our red quadrilateral. I'll pick this vertex. And there's only one other vertex that it's not already connected to. So I connect it. And I can see again, we have 2 triangles. We'll go to our yellow quadrilateral. Again, I'll pick this vertex and connect it across, 2 triangles. And finally down here at the bottom to our brown quadrilateral, and I'll pick this vertex, and this is kind of a tricky one, but it's going to look like that. And we have 1, 2 triangles. So each quadrilateral was cut into 2 triangles. All right, how many triangles can a pentagon be cut into? So now we have 5-sided polygons, pentagons, and let's go ahead and go through this. So I'm going to pick this vertex, and I will connect it here and here. And you can see we have 1, 2, 3 triangles. All right, let's go over to our purple pentagon. I'm going to go ahead and pick that vertex and connect it there. And there, that's 1, 2, 3 triangles. Go to my blue pentagon. I'll pick this vertex and I'll connect it there and there. That's 1, 2, 3 triangles. And finally the green pentagon. I'll go here and I'll connect it there and there. That's 1, 2, 3 triangles. So each of our pentagons could be cut into 3 triangles. Okay, so let's take a look at a hexagon, a heptagon, an octagon, and a dodecagon. So this is going to get a little more complicated the more sides we get, but let's give it a shot. So I'm going to pick this vertex, and I'm going to connect it there, there, and there. So I have 1, 2, 3, 4 triangles. All right, let's go over to our heptagon. Connect it there, 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 and there. That's 1, 2, 3, 4, 5 triangles. Okay, have you seen a pattern starting here? Octagon. Pick this vertex. Connect it once, 2. There's another one, and another one. So that's 1, 2, 3, 4, 5, 6. Triangles that the octagon can be broken into. And now the dodecagon. So let's see how this plays out here. I'm going to pick that vertex and I'm going to connect it there, 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 and one more right there. Kind of looks like a seashell. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this one over here is 10. So the dodecagon, which has 12 sides, can be cut into 10 triangles. So you're probably wondering what we're doing, right? Well, we are using some inductive reasoning, because we're trying to find a pattern. When we take a polygon and we cut it into triangles, is there a pattern that relates how many sides the polygon has and how many triangles it can be cut into? So what is the relation between the number of sides, angles, and triangles in a polygon? Well, we had all these examples, right? Triangle, quadrilateral, pentagon, and so on. Of course, the number of angles in each of those is equal to the number of sides. So those all correspond, right? So for example, this one I'm looking at, a triangle has 3 sides and 3 angles, right? A dodecagon has 12 sides and 12 angles. Now, if we connect our inductive reasoning, how many triangles does each of these things break into or cut into? So we saw that a triangle, while it has 3 sides, is cut into just 1 triangle. It's not cut at all, actually, right? A quadrilateral is cut into 2 triangles. A pentagon is cut into 3 triangles. Notice that the number of triangles that the polygon is cut into is always 2 less than the number of sides and the number of angles of the polygon. Now we can use this information to come up with what we call the Polygon Sum Conjecture. It's a formula that tells us how many degrees are in a polygon, any polygon, right? No matter how many sides. So the sum of the measures of the n interior angles of an n-gon is, here we go, ready? 180 degrees times n minus 2. Now let's think about where this comes from. If n is the number of angles, then it's also the number of sides, because we know that each polygon has the same number of angles as it does sides. And we can break each polygon into 2 less triangles than there are number of sides. So that's where n minus 2 comes from. And of course, we know that each triangle has a sum of 180 degrees. So essentially what we're doing to get this formula, we're taking the sum of the angles of a single triangle times the number of triangles that a polygon can be broken into. And this will give us the total number of degrees of any polygon, where n is the number of sides of the polygon. So this is our Polygon Sum Conjecture. And we can use this formula moving forward to find the sum of any of the angles of any polygon. And furthermore, we can use this formula moving forward to problem solve.